On December 8, 1995, at 1947, a prototype fast breeder reactor operated exactly as its designers intended. Liquid sodium circulated through 3 independent loops at 505 degrees Celsius. Temperature sensors reported normal variations. Leak detection systems remained quiet. The reactor had been designed with multiple redundant monitoring systems specifically to prevent the kind of failure that was, at that precise moment, already underway. A thermocouple, a small steel tube designed to protect temperature sensors from the corrosive sodium environment, had been vibrating in the flowing coolant for months. The vibrations were within design parameters. The temperature readings remained accurate. The structural integrity monitoring showed no anomalies. Every instrument performed its intended function correctly. Yet this same instrumentation system was fundamentally incapable of detecting the one failure mode that would actually occur: high cycle fatigue of a component placed directly in the sodium flow path. The designers had assumed that sophisticated monitoring would reveal problems before they became critical. Instead, the monitoring architecture created a systematic blind spot where small mechanical failures could progress to system-wide consequences without triggering any alarm. This is not an account of negligence or inadequate safety culture. It is the forensic examination of how a reactor's information systems functioned precisely as designed while making critical failures invisible to operators who acted rationally on technically accurate but systematically incomplete data. The Monju prototype fast breeder reactor represented the culmination of decades of Japanese nuclear engineering ambition. Designed to generate 280 MWe from 714 MWt thermal output, the facility embodied a sophisticated approach to nuclear fuel breeding that required unprecedented precision in thermal monitoring. The reactor core contained mixed plutonium-uranium oxide fuel assemblies, surrounded by uranium blankets, with the entire system cooled by liquid sodium, flowing at temperatures reaching 529 degrees Celsius at the reactor outlet. The fundamental design philosophy governing Monju's instrumentation architecture reflected a conviction that comprehensive measurement equals comprehensive control. Thermal output, coolant flow rates, temperatures at multiple points throughout each loop, and pressure differentials across major components were continuously monitored through an extensive network of sensors. The secondary heat transport system, where the eventual failure would occur, incorporated temperature measurement at the outlet of each intermediate heat exchanger to ensure precise thermal balance across the 3 independent loops. This measurement imperative created an immediate engineering conflict. Liquid sodium, while an excellent heat transfer medium, proves extraordinarily hostile to instrumentation. At operating temperatures exceeding 500 degrees Celsius, direct contact between sodium and most sensor materials results in rapid corrosion. The solution adopted at Monju, consistent with fast reactor practice worldwide, involved housing temperature sensors within protective wells that extended into the sodium flow stream while isolating the sensing elements from direct sodium contact. The thermocouple wells installed in Monju's secondary heat transport system followed design guidance provided by the American Society of Mechanical Engineers Performance Test Code PTC 19.3. This code, developed for conventional industrial applications, recommended tapered well geometries to minimize flow disturbance and prevent resonant vibrations that could damage sensors through vortex shedding. The specific guidance called for gradual diameter reduction toward the well tip to ensure smooth flow transition and avoid sharp discontinuities that might create flow separation. However, the wells installed at Monju incorporated a sharp taper geometry with an abrupt 120-degree angle transition near the tip. This deviation from recommended practice occurred because the design team prioritized thermal response time over hydrodynamic considerations. A sharp taper positioned the sensing element closer to the outer pipe wall boundary layer, theoretically improving temperature measurement accuracy by reducing thermal lag. The ASME code addressed vortex-induced vibrations that could cause resonant oscillations leading to immediate component failure, but the sharp taper geometry at Monju created conditions for a different failure mechanism entirely: high cycle fatigue, resulting from small amplitude vibrations in multiple directions simultaneously. While the code's guidance prevented dramatic resonant failures, It did not address the cumulative effects of sustained low-amplitude oscillations that could initiate fatigue cracks over extended operating periods. This design choice reflected a broader assumption embedded throughout Monju's instrumentation philosophy, that monitoring systems could provide sufficient warning of developing problems to prevent component failures. The assumption proved reasonable for most anticipated failure modes. Thermal transients, flow blockages, pump failures, and other major system disturbances would indeed generate detectable precursor signals through the extensive sensor network. But mechanical degradation of the monitoring components themselves created a monitoring paradox. The sensors remained functional throughout the degradation process, continuing to provide accurate temperature readings even as their structural support deteriorated. The thermocouple well could develop fatigue cracks, propagate those cracks over months of operation, and approach complete structural failure while the temperature measurement remained within normal operating tolerances. The instrumentation design philosophy also reflected assumptions about failure mode probability and consequence. Design attention focused on events that could damage the reactor core or release radioactivity scenarios where thermal monitoring provided essential protection. Secondary system component failures, while operationally disruptive, posed minimal radiological risk and received correspondingly less design attention. This risk prioritization made engineering sense within the established safety framework. Sodium leaks in the secondary system could not release fission products to the environment. Primary system inventory remained completely isolated from secondary system sodium through the intermediate heat exchanger boundaries. From a radiological perspective, secondary system component failures represented nuisance events rather than safety challenges. Yet this same risk assessment created systematic blind spots in component monitoring. Primary system sensors received redundant protection and extensive condition monitoring precisely because their failure could mask core damage. Secondary system sensors, considered less safety critical, operated with minimal condition monitoring beyond the temperature data they provided. The thermal instrumentation strategy at Monju also assumed that temperature measurement accuracy was the primary sensor performance metric. Design optimization focused on minimizing thermal response time and maximizing measurement precision. Mechanical durability, while considered during design, received secondary priority compared to thermal performance characteristics. This optimization approach proved entirely reasonable given the performance requirements for fast reactor operation. Breeding ratio calculations, thermal efficiency assessments, and operational safety margins all depended on precise temperature measurement throughout the heat transport systems. Small errors in temperature measurement could significantly impact operational performance and safety analysis accuracy. The assumption that thermal performance and mechanical durability were independent design variables, however, created unexpected interactions. Geometry optimized for thermal response created mechanical stress concentrations that accelerated fatigue crack initiation. Sharp corners that improved thermal coupling also served as crack nucleation sites under vibrational loading. Regulatory oversight of Monju's design reflected these same assumptions about monitoring system capabilities. Design approval processes verified that instrumentation coverage met requirements for detecting anticipated operational transients and accident scenarios. The extensive sensor network provided confidence that operators would receive adequate warning of developing problems across all credible failure modes. But regulatory review focused on sensor functionality rather than sensor durability. Verification protocols confirmed that temperature measurements met accuracy requirements under design conditions. Component qualification testing demonstrated sensor performance under thermal and chemical stress. However, systematic evaluation of sensor mechanical integrity under combined thermal, chemical, and vibrational loading received limited attention. The regulatory framework reflected broader industry assumptions that sophisticated monitoring systems could provide adequate protection against unforeseen failure modes. If operators received accurate data from multiple independent sensors, they should be capable of recognizing and responding to any significant system degradation before irreversible damage occurred. This confidence in monitoring system capabilities extended beyond nuclear applications to complex industrial systems generally. The emerging field of advanced process control promised that comprehensive data collection and analysis could optimize performance, while preventing failures across a wide range of applications. Fast breeder reactors represented the cutting edge of this monitoring philosophy applied to nuclear technology. The design team's confidence in monitoring system capabilities was reinforced by successful operation of other fast reactor facilities worldwide. Experimental reactors in multiple countries had demonstrated the feasibility of sodium-cooled systems with extensive temperature monitoring. Component failures had occurred in these facilities, but monitoring systems had provided adequate warning to prevent serious consequences. However, the design basis for Monju's instrumentation reflected operational experience from smaller experimental facilities with different geometries, flow rates, and sensor placements. Scaling effects and installation-specific considerations received limited attention during design review. The assumption that proven monitoring principles would transfer directly to Monju's specific configuration proved incorrect in this critical instance. The philosophical foundation underlying Monju's design was that engineering problems had engineering solutions and that sufficient monitoring could overcome any technical challenge. This optimism was not misplaced. The reactor would eventually restart safely after design modifications addressed the identified failure mechanism. But the initial design phase underestimated how monitoring system design choices could create failure modes that the monitoring system itself could not detect. As Monju approached initial criticality in April 1994 and began power ascension testing through 1995, operators gained confidence in the extensive instrumentation system. Temperature measurements tracked predicted values, flow rates remained stable, pressure measurements confirmed thermal hydraulic modeling predictions. Every indication suggested that the design philosophy of comprehensive monitoring was functioning exactly as intended. The monitoring system was, in fact, functioning perfectly. It was providing accurate data about the thermal state of the sodium coolant while remaining completely unable to detect the mechanical degradation that would ultimately cause its own failure. The control room at Monju on December 8, 1995, reflected decades of human factors engineering applied to nuclear reactor operations. Banks of analog instruments displayed primary loop temperatures, flow rates, and pressure measurements with precision dials calibrated to tenths of degrees and fractions of flow percentages. Digital displays provided backup readings and trend information. Alarm panels were organized by system priority, with reactor protection system alarms positioned for immediate operator attention. The human-machine interface design embodied a fundamental assumption about how operators would interact with a sodium-cooled reactor, that thermal management represented the primary operational challenge, and that adequate thermal information would enable operators to maintain safe plant conditions under all circumstances. This assumption shaped every aspect of the control room layout, alarm prioritization, and procedure development. Training programs for Monju operators reflected this thermal management focus. Extensive simulator time was devoted to managing thermal transients, responding to flow variations, and maintaining proper temperature distributions across the core and heat transport systems. Operators became highly skilled at interpreting thermal trends and implementing procedural responses to thermal upsets. Secondary system operations received correspondingly less training emphasis. While operators understood the function of the intermediate heat exchangers and steam generators, detailed knowledge of component mechanical condition monitoring was not considered essential for safe operation. Secondary system temperature monitoring was viewed primarily as an operational parameter for thermal efficiency optimization rather than a safety-critical function. The operating procedures in effect on December 8, 1995, provided detailed guidance for managing sodium leak events, but these procedures reflected assumptions about how leaks would be detected and characterized. The emergency operating procedures categorized sodium leaks by size: small, medium, and large, with response actions scaled to leak severity. Small leaks permitted continued operation while monitoring leak progression. Medium leaks required power reduction and preparation for shutdown. Large leaks mandated immediate reactor trip and emergency response activation. However, the leak classification system assumed that leak size could be determined from available instrumentation, temperature measurements, leak detection system responses, and visual observations were expected to provide sufficient information for leak characterization. The procedures did not address situations where multiple detection systems provided ambiguous or contradictory information about leak severity. Operator training emphasized procedural compliance and conservative decision-making. When uncertain about plant conditions, operators were instructed to assume more severe conditions and implement correspondingly conservative responses. This training philosophy generally enhanced safety by encouraging operators to err on the side of caution when interpreting ambiguous information. But the conservative training approach created operational tensions when applied to sodium leak events. Immediate reactor shutdown for minor leaks could cause unnecessary thermal stress to plant components. Sodium freezing in lines during rapid shutdown posed operational risks that had to be balanced against leak response requirements. Operators were trained to make these judgment calls based on available information about leak characteristics. The control room alarm system architecture reflected the same thermal management priorities embedded throughout Monju's design. High-priority alarms included reactor protection system actuations, primary coolant flow variations, and core temperature deviations. Secondary system alarms received lower priority classification, appearing on different alarm panels with less urgent audio and visual indications. This alarm prioritization made operational sense, given the safety significance of different systems. Primary system problems could threaten core cooling and potentially release radioactivity. Secondary system problems, while operationally disruptive, posed minimal safety consequences under design basis conditions. Alarm hierarchy appropriately directed operator attention to safety-significant events first. However, the alarm prioritization system assumed that secondary system problems would remain secondary in their operational impact. Component failures in the secondary heat transport system were expected to be manageable through normal operational procedures without challenging primary system operation or threatening plant safety. The assumption proved incorrect when secondary system component failure initiated a sequence that required emergency response procedures and ultimately led to manual reactor trip. The alarm system design had not anticipated that small component failures could escalate through operational complications to require emergency actions. Control room ergonomics further reinforced the thermal management focus. Temperature measurement displays were positioned for optimal operator visibility. Trend recorders provided continuous documentation of thermal performance. Flow rate indicators were readily accessible for thermal balance calculations. The physical layout of instruments guided operator attention toward thermal parameters as the primary indicators of plant condition. Mechanical condition indicators for secondary system components received less prominent placement. Vibration monitoring systems, where they existed, displayed on auxiliary panels that operators consulted less frequently. Component condition information was typically reviewed during planned maintenance windows rather than monitored continuously during operation. The information display architecture reflected an implicit assumption that mechanical degradation would proceed slowly enough to be detected during scheduled maintenance inspections. Continuous mechanical condition monitoring was not considered necessary for components that did not directly affect reactor safety. This assumption proved incorrect for components subject to flow-induced vibration under normal operating conditions. Operator communication protocols reflected the thermal management priorities embedded in training and procedures. Shift turnover briefings emphasized thermal performance parameters, planned thermal transients, and thermal margin assessments. Mechanical condition information was typically communicated through maintenance work order systems rather than operational briefings. This communication approach ensured that operators maintained awareness of thermal challenges while remaining less informed about mechanical degradation trends. Component vibration levels, structural inspection results, and mechanical performance assessments were managed through separate organizational channels that did not routinely interface with operational decision-making. The maintenance organization structure also reflected assumptions about failure mode priorities. Maintenance scheduling focused on components whose failure could affect reactor safety or thermal performance. Secondary system component maintenance received lower priority scheduling, with extended intervals between inspections for components considered less safety significant. Maintenance procedures for thermocouple wells and similar secondary system components emphasized verification of thermal performance rather than structural condition assessment. Calibration checks confirmed that temperature readings remained within specification tolerances. Functional testing verified that sensor response times met requirements. Structural integrity assessments were typically limited to visual inspections during system outages. The maintenance approach reflected reasonable resource allocation given the safety significance of different components. Limited maintenance resources were appropriately focused on safety-critical components that required extensive surveillance. Secondary system components that posed minimal safety risk could reasonably receive less frequent and less detailed maintenance attention. However, this approach assumed that components could be reliably categorized as safety significant or non-safety significant, without considering potential interaction effects. A component failure that was individually non-safety significant could still initiate operational sequences that challenged safety systems through indirect pathways. Training scenarios used for operator qualification and continuing education reflected the same assumptions about failure mode likelihood and consequences. Simulator exercises emphasize thermal transients, coolant flow variations, and reactor protection system challenges. Scenarios involving secondary system component failures were typically brief exercises focused on leak isolation and thermal impact mitigation. Operators received extensive training on managing primary system transients because these events posed direct safety challenges. Secondary system events received less training attention because they were expected to remain operationally manageable without threatening reactor safety. This training allocation was technically justified but created operational blind spots when secondary system failures initiated complex response sequences. The emergency response organization structure reflected assumptions about how plant emergencies would develop and progress. Emergency response procedures anticipated that radiological emergencies would result from primary system failures or loss of core cooling. Secondary system events were classified as operational occurrences rather than emergencies unless they progressed to threaten primary system integrity. Classification system appropriately prioritized response resources for events with the highest safety consequences. Emergency response teams focused on scenarios that could result in radioactivity release or challenge public safety. Operational problems that remained contained within plant boundaries received correspondingly less urgent response classification. But the classification system assumed that event progression could be predicted based on initial system involvement. An event that began in the secondary system was expected to remain a secondary system problem unless specific escalation criteria were met. The procedures did not adequately address situations where secondary system problems initiated operational complications that challenged multiple systems simultaneously. Organizational interfaces between operations, maintenance, and engineering reflected the thermal management priorities embedded throughout Monju's design. Operations staff maintained detailed knowledge of thermal performance requirements and thermal transient management. Maintenance staff focused on component reliability for safety-significant systems. Engineering staff supported thermal analysis and safety analysis activities. These organizational specializations ensured adequate expertise in each technical area while creating communication challenges when problems crossed organizational boundaries. Mechanical degradation of instrumentation components involved operational impacts, maintenance implications, and engineering analysis requirements that required coordination across organizational interfaces. The information management systems in use at Monju reflected assumptions about what types of data required operational attention versus engineering analysis. Thermal performance data was immediately available to operators through control room displays. Component condition data was typically stored in maintenance databases that required separate access procedures. This information architecture supported efficient operational decision-making by presenting operationally relevant information through streamlined interfaces. Operators could quickly assess thermal conditions without being overwhelmed by detailed component condition information that did not directly affect immediate operational decisions. However, the information separation assumed that operational and mechanical condition data could be independently analyzed without losing important correlations. Component mechanical degradation that affected operational parameters required integrated analysis across multiple information systems to recognize developing problems. As the afternoon shift began at Monju on December 8, 1995, these latent conditions had created an operational environment where small component failures could progress to complex emergency situations without adequate early warning. Operators possessed excellent skills for thermal management and extensive knowledge of reactor safety systems. They had received appropriate training for anticipated failure modes and possessed adequate procedures for managing expected operational challenges. But the combination of thermal management focus, alarm prioritization, information architecture, and organizational structure had created systematic blind spots where mechanical degradation could proceed undetected until it initiated operational sequences that exceeded the scope of normal operational procedures. Following a program shutdown, Monju restarted operation on December 6, 1995. The restart sequence proceeded according to established procedures, with primary coolant flow established through all three loops, secondary system sodium circulation initiated, and thermal power gradually increased toward the target level for the planned 40% electric power test. By December 8, thermal power had reached 43% as operators prepared to conduct a plant trip test as part of the Power Ascension program. At 1947 on December 8, 1995, the first indication of system deviation appeared on the control room displays. A high sodium temperature alarm sounded at the outlet of the intermediate heat exchanger in secondary heat transport system Loop C. The temperature elevation was modest within the range that could indicate normal operational variation or minor system imbalance. Operators noted the alarm, but did not immediately classify it as an emergency condition. Approximately simultaneously with the temperature alarm, smoke detectors in the SHES Loop C piping room activated, generating fire alarm indications in the control room. The coincidence of thermal and fire detection alarms in the same system loop immediately suggested a correlation between the two events. Within minutes, sodium leak detection alarms confirmed that sodium had escaped from the Loop C piping and was reacting with atmospheric air in the confined piping room. These first alarm indications marked the moment when plant conditions diverged from operator understanding of system state. The temperature measurement that triggered the initial alarm was accurate. Sodium temperature at the IHX outlet had indeed increased. The fire detection system correctly identified combustion products in the piping room atmosphere. The leak detection system properly confirmed sodium presence where none should exist. Every instrument functioned correctly, yet the combination of accurate signals provided operators with an incomplete picture of what had actually occurred. The temperature increase resulted from sodium escaping through a failed thermocouple well, but no instrument could directly identify this specific failure mechanism. The fire detection responded to sodium combustion, but could not quantify the leak rate or predict leak progression. The leak detection confirmed sodium presence, but provided no information about the failure location or structural condition of the affected component. Microscopic examination would later reveal that the thermocouple well failure had been months in development. Fatigue crack initiation occurred during an early period of 100% flow operation, when vortex shedding around the sharp taper geometry created oscillating stress concentrations at the root of the tapered section. The crack propagation proceeded gradually through subsequent operation at various power levels, with the crack front advancing through the well wall thickness at rates determined by the stress intensity and material properties under sodium environment conditions. The crack propagation process remained entirely invisible to plant instrumentation throughout its development. Temperature measurement accuracy was unaffected because the thermocouple itself remained intact within the protective well. Flow rate measurements showed no variation because the crack opening was initially too small to affect bulk coolant flow. Pressure measurements remained normal because the crack did not initially penetrate completely through the well wall. Flow-induced vibration analysis conducted after the incident revealed that the well tube experienced symmetric vortex shedding at the operating sodium flow rate of 5 meters per second. The sharp taper geometry created flow separation that generated alternating vortices on both sides of the well, producing oscillating forces in multiple directions simultaneously. Unlike resonant vibrations that create large amplitude oscillations at specific frequencies, The vortex shedding produced small amplitude vibrations across a range of frequencies that accumulated fatigue damage over extended operating periods. The fatigue crack analysis, based on metallurgical examination of the fracture surface and operational history reconstruction, indicated that crack initiation occurred at stress concentration points created by the 120-degree angle transition in the well geometry. The combination of vibrational loading and thermal stress created crack nucleation sites that began accumulating damage during early high-power operation. Material analysis revealed that the crack propagation proceeded through mechanisms consistent with high-cycle fatigue in stainless steel under sodium environment. The fracture surface exhibited characteristic features including crack initiation regions, progressive crack growth areas with striation patterns, and final fracture zones with dimpled surfaces typical of ductile failure modes. The timing of the final failure during 40% power operation initially appeared inconsistent with a fatigue mechanism that should worsen with increased vibrational loading. However, detailed analysis revealed that the crack had propagated to near-critical dimensions during previous high-power operation. The final fracture occurred when remaining wall thickness could no longer support even the reduced loads present during partial power operation. This failure timing created additional diagnostic confusion for operators. The plant was operating at reduced power when the failure occurred, with all major parameters stable and within normal operating ranges. There had been no recent transients, no unusual operational events, and no maintenance activities in the affected system. From the operator's perspective, the failure occurred during benign operating conditions that should have posed minimal stress to plant components. The location of the failure also contributed to diagnostic complexity. The thermocouple well was positioned near the outlet of the intermediate heat exchanger in a region of the secondary heat transport system where high temperatures and flow rates created challenging operating conditions for instrumentation components. However, identical wells in the same locations in loops A and B continued operating normally, suggesting that the failure was not simply a result of excessive operating conditions. When the thermocouple well tip separated from the remaining structure, it created a direct pathway for sodium to escape from the pressurized secondary loop into the piping room atmosphere. The leak rate was determined by the pressure differential across the opening and the effective flow area of the fracture. Initial leak rate was modest because the fracture opening was relatively small, but sodium continued to flow as long as the loop remained pressurized. The escaped sodium immediately began reacting with atmospheric moisture and oxygen to form sodium hydroxide, sodium oxide, and other chemical compounds. These reactions are highly exothermic, generating heat and light that triggered the fire detection systems. The reaction products also created the distinctive white smoke that operators would observe when they opened the piping room door to assess conditions. Chemical analysis of the deposits recovered from the piping room confirmed the presence of various sodium compounds consistent with high-temperature oxidation reactions. The deposit distribution pattern indicated that sodium had been ejected from the leak point with sufficient energy to distribute across the room, with the heaviest concentrations forming a semicircular mound approximately 3 meters in diameter and 30 centimeters high directly beneath the failed thermocouple well. The ventilation system design for the HTS piping rooms assumed that any airborne contamination would be diluted and removed through normal air circulation. However, the sodium fire generated reaction products faster than the ventilation system could remove them, creating a buildup of combustion products that triggered multiple fire detection devices throughout the affected room and adjacent areas. Operator response to the initial alarm indications followed established procedures for small sodium leaks. The emergency operating procedures called for continued operation with enhanced monitoring when leak indications suggested a small leak that posed no immediate threat to plant safety. Operators began the prescribed monitoring activities while assessing whether conditions warranted transition to more restrictive emergency procedures. The procedural response reflected sound operational judgment based on the information available at the time. The temperature alarm could have resulted from minor flow imbalances that required only minor adjustments. Fire detection systems occasionally generated false alarms from dust or other environmental factors. Even confirmed small sodium leaks could often be managed through controlled power reduction while maintaining plant operation. However, the procedures assumed that leak severity could be determined from available instrumentation and visual observations. The actual failure mechanism produced ambiguous indications that did not clearly fit the established leak classification categories. Operators were required to make severity judgments based on incomplete information about a failure mode that had not been anticipated during procedure development. Plant conditions at the time of the failure reflected normal operational parameters throughout the facility. Primary coolant flow rate was 5.1 million kilograms per hour through each of the 3 primary loops. Reactor inlet temperature was 397 degrees Celsius, with outlet temperature at 529 degrees Celsius. Secondary system flow rates were 3.7 million kilograms per hour through each secondary loop, with IHX inlet temperature at 325 degrees Celsius and outlet temperature at 505 degrees Celsius. The thermal hydraulic conditions in the failed Loop C were identical to those in Loops A and B, which continued operating normally throughout the event. This operational consistency reinforced operator assessment that the problem was localized to Loop C and did not represent a systematic failure mode that could affect the other loops. Primary system operation remained completely normal throughout the secondary system event. Reactor power level, coolant flow rates, and temperature distributions showed no response to the secondary system disturbance. This operational independence confirmed that the reactor safety systems were functioning properly, and that the secondary system problem posed no immediate threat to reactor safety. The first inspection of the SGS Loop C piping room occurred at 2050, when operators partially opened the door to assess conditions inside the room. They observed an increase in white smoke compared to earlier observations, indicating that the reaction between escaped sodium and atmospheric air was continuing. This observation confirmed that sodium was continuing to leak from the system, and that the leak had not self-sealed. The visual confirmation of continuing sodium leakage prompted operators to implement more restrictive emergency procedures. Electric power generation was stopped at 2115, and the reactor was manually tripped at 2120. These actions were conservative responses to the confirmed leak conditions and reflected appropriate operational judgment to prevent leak escalation while ensuring adequate reactor cooling capability. The decision timeline from initial alarm to reactor trip reflected careful operational assessment rather than precipitous action. Operators spent approximately 90 minutes evaluating leak severity, consulting procedures, and implementing monitoring actions before concluding that reactor shutdown was necessary. This deliberate approach demonstrated appropriate procedural compliance and conservative decision-making under uncertain conditions. However, the assessment period also reflected the fundamental limitation in available diagnostic information. Operators could confirm that a sodium leak was occurring and that leak conditions were not improving, but they could not determine the failure mechanism, predict leak progression, or assess the structural condition of the failed component. The decision to trip the reactor was based on prudent operational conservatism rather than specific technical assessment of the failure consequences. Immediately after reactor trip, decay heat removal was established through the auxiliary cooling system for all 3 secondary loops. This configuration provided adequate cooling capacity, while allowing operators to begin isolating the affected Loop C decay heat levels at 43% power required substantial cooling capacity, but the 2 intact secondary loops provided sufficient heat removal capability with ACS support. The reactor trip and subsequent cooling system configuration represented the transition point where operators gained control over plant thermal conditions while beginning the process of isolating the failed component. From this point forward, plant response would be determined by procedural actions rather than by the progression of the initiating failure. The failed thermocouple well tip was eventually located using a CCD camera inserted into the sodium inlet header of the superheater, where it was found in the distributor at the top of the superheater. The discovery location confirmed that the separated tip had been transported through the secondary loop piping by sodium flow, eventually coming to rest in a region where flow velocity decreased sufficiently for the component to settle. Recovery of the separated tip using a specially developed gripper on April 24, provided physical evidence that confirmed the failure mechanism analysis. The recovered component exhibited fracture surface characteristics consistent with fatigue failure, validating the theoretical analysis of flow-induced vibration and stress concentration effects. At the moment of initial alarm activation, plant instrumentation was providing accurate information about system conditions while remaining incapable of diagnosing the specific failure that was producing those conditions. This fundamental limitation in diagnostic capability would shape every subsequent decision as operators worked with technically correct but systematically incomplete information about the actual system state. The fracture of the thermocouple well tip created a direct communication path between the pressurized secondary heat transport system and the atmospheric environment of the piping room. At the moment of final separation, sodium at approximately 505 degrees Celsius and elevated pressure began flowing through the newly created opening, at a rate determined by the pressure differential and the effective flow area of the fracture geometry. The mass flow rate of escaped sodium was governed by fundamental fluid mechanics principles applied to the specific conditions present in SHTS Loop C. Secondary system pressure at the IHX outlet location was approximately 0.1 MPa above atmospheric pressure, providing the driving force for sodium ejection through the fractured well opening. The irregular geometry of the fatigue fracture surface created a complex flow path that influenced both flow rate and spray pattern of the escaping sodium. Computational fluid dynamics analysis conducted during the post-incident investigation revealed that sodium escaping through the fractured thermocouple well was ejected with sufficient velocity to distribute throughout the piping room. The high-temperature sodium immediately began oxidizing upon contact with atmospheric oxygen and moisture, creating the exothermic chemical reactions that generated heat, light, and gaseous products detected by the fire protection systems. The chemical physics of sodium-air reactions proceeded according to well-established thermochemical principles. Primary oxidation reactions produced sodium oxide, Na2O, and sodium hydroxide, NaO, as the dominant products, with reaction rates enhanced by the high surface area created when liquid sodium was dispersed as droplets and films throughout the piping room. Secondary reactions between sodium compounds and atmospheric carbon dioxide produce sodium carbonate, Na2CO3, and other derivative compounds. These oxidation reactions are highly exothermic, releasing approximately 400 kilojoules per mole of sodium oxidized. The energy release rate was sufficient to raise local air temperatures and generate visible light emission that triggered optical fire detection systems throughout the affected area. The reaction also consumed atmospheric oxygen and generated water vapor, carbon dioxide, and other gaseous products that altered the atmospheric composition within the confined piping room space. The piping room ventilation system was designed to maintain adequate air circulation for personnel access and equipment cooling under normal operating conditions. However, the system was not designed to manage the gas generation rates and thermal loading created by a sustained sodium fire. Ventilation airflow rates were quickly overwhelmed by the combination of thermal buoyancy effects and gas generation from the ongoing oxidation reactions. Fire detection system response reflected the design sensitivity of the installed equipment to the specific products generated by sodium combustion. Optical detectors responded to visible light emission from the high-temperature oxidation reactions. Smoke detectors responded to particulate matter entrained in the rising gases. The detection system functioned exactly as designed, providing rapid identification of combustion conditions in the protected space. However, fire detection system design assumptions did not include provision for determining the source of ignition or estimating the quantity of combustible material involved. The detection systems could confirm that combustion was occurring and estimate the general location based on detector response patterns, but could not distinguish between different types of fires or predict fire progression characteristics. The leak detection systems installed in the SHTS piping rooms were designed to identify the presence of sodium in areas where sodium should not exist under normal operating conditions. Detection was accomplished through conductivity measurements that could identify the highly conductive sodium compounds formed when escaped sodium reacted with atmospheric moisture. Leak detection system response confirmed sodium presence, but provided no quantitative information about leak rates or accumulated quantities. The systems were designed as binary indicators, sodium detected or not detected, rather than as measurement devices capable of characterizing leak severity or progression trends. Temperature measurements throughout SHTS. Loop C remained within normal operating ranges throughout the initial phase of the sodium leak. The thermocouple that had been housed within the failed well continued providing accurate readings until the supporting structure separated completely. Other temperature measurements in the loop showed slight variations as operators began implementing leak response procedures, but no measurements indicated abnormal thermal conditions that would suggest major system disruption. This continued normal thermal performance reinforced operator assessment that the leak was relatively small and localized. Major sodium leaks would be expected to cause significant temperature variations as system inventory was lost and thermal balance was disrupted. The absence of major thermal transients suggested that the leak rate was manageable and that system integrity was not seriously compromised. Pressure measurements in SGS Loop C similarly remained within normal operating ranges. The leak flow rate was insufficient to cause detectable pressure drop in the large volume secondary loop. System pressure was maintained by the secondary sodium pumps, which continued operating normally and compensated for the small inventory loss through normal pressure control mechanisms. The sodium inventory in each secondary loop was approximately 760 tons, providing substantial margin for small leaks without affecting system operation. Leak rates on the order of kilograms per hour would not significantly impact system inventory or pressure control. Only leaks involving substantial fractions of total system inventory would create detectable pressure or flow rate variations. Flow rate measurements in SGS Loop C initially showed no significant variation from normal operating values. Secondary loop flow rate was maintained at approximately 3.7 million kilograms per hour by the loop circulation pump, which continued operating normally throughout the initial leak period. The pump was capable of maintaining design flow rates despite the small inventory loss through the thermocouple well leak. As the leak continued, flow measurement stability provided additional confirmation that the leak was relatively small compared to total system flow rates. Major component failures that created large leak areas would be expected to cause detectable flow rate variations as system hydraulics were disrupted. The continued stable flow measurements reinforced assessment that the leak was manageable through operational procedures. The accumulation of sodium compounds on the piping room floor proceeded according to gravitational, settling, and chemical reaction kinetics. Sodium droplets ejected through the fracture opening followed ballistic trajectories determined by their initial velocity and gravitational acceleration. Upon impact with room surfaces, the sodium spread according to surface tension and wetting characteristics, then began oxidizing through contact with atmospheric components. Post-incident examination revealed that approximately 1 cubic meter of solid sodium compounds had accumulated in a semicircular pattern beneath the failed thermocouple well location. The compound distribution indicated that sodium had been ejected with sufficient energy to travel several meters from the leak point before settling and oxidizing. The heaviest accumulations occurred directly beneath the leak source, with lighter distributions extending throughout the room according to airflow patterns and splash trajectories. Chemical analysis of the accumulated compounds confirmed that oxidation reactions had proceeded to completion for sodium that had sufficient contact time with atmospheric components. Compounds closest to the leak point showed higher concentrations of incompletely oxidized sodium, indicating that reaction rates were limited by oxygen availability rather than reaction kinetics in regions with high sodium concentrations. The ventilation ductwork in the piping room sustained damage when sodium compounds came into contact with the aluminum ducting material. Sodium compounds are highly reactive with aluminum, creating localized heating that weakened duct walls and created openings that further disrupted airflow patterns. This damage contributed to the accumulation of combustion products within the piping room atmosphere. Steel walkway gratings beneath the piping sustained similar damage where sodium compounds accumulated and reacted with the grating material. The compounds created localized corrosion that weakened grating structures and created openings where sodium globules collected. This damage pattern provided physical evidence of sodium distribution throughout the vertical space of the piping room. The interconnection between the Sheech Loop C piping room and the adjacent steam generator room allowed sodium compounds to migrate beyond the immediate leak area. Airflow patterns and gravitational settling carried compounds through connecting passages, creating contamination throughout the connected spaces. This distribution pattern complicated cleanup operations but provided additional evidence of leak progression and compound transport mechanisms. Thermal analysis of the piping room environment during the leak event revealed that heat generation from sodium oxidation reactions raised local air temperatures and created thermal buoyancy effects that influenced compound distribution patterns. Hot gases rose toward the ceiling and were dispersed by ventilation airflow, while denser compounds settled toward floor areas where they continued reacting with atmospheric components. The heat generation rate from sodium oxidation was sufficient to create localized thermal stress in room structures, but insufficient to threaten structural integrity of major components. Concrete walls and steel structures were designed to withstand much higher thermal loading, and the sodium fire did not approach the thermal intensity that would challenge structural materials. As operators began implementing leak response procedures, the primary objective became stopping the sodium flow while maintaining adequate reactor cooling. This required isolating SHES Loop C, while ensuring that the remaining two loops could provide sufficient heat removal capacity for decay heat levels present after reactor shutdown. The loop isolation process involved closing valves to prevent further sodium circulation through the damaged component while draining sodium inventory to remove the driving pressure for continued leakage. However, sodium drainage required careful temperature management to prevent sodium solidification in piping systems, creating operational constraints that influenced response timing and sequencing. Decay heat removal during the loop isolation process was accomplished through the auxiliary cooling system operating with the two intact secondary loops. This configuration provided adequate cooling capacity for the thermal loads present, but required careful thermal management to ensure proper heat removal distribution and prevent overheating in the operating loops. The successful isolation of SHDS Loop C and establishment of stable decay heat removal marked the end of the active leak progression phase. From this point forward, the event transitioned from an evolving emergency to a controlled shutdown and cleanup operation. The failure mechanism had been isolated, even though the specific component failure and root cause would not be determined until detailed investigation could be conducted. The physics of the failure progression revealed how small mechanical failures could create complex operational challenges through interaction with system chemistry and atmospheric conditions. The failure sequence demonstrated that accurate monitoring of bulk system parameters could mask localized component failures until they initiated chemical and thermal processes that created detectable secondary effects. Following the manual reactor trip at 2120 on December 8, 1995, Monju operators faced the challenge of maintaining adequate decay heat removal while isolating the failed component in SHTS Loop C. The reactor shutdown had eliminated active power generation, but substantial decay heat continued to be produced by fission product decay within the reactor core. This thermal load required continuous cooling to prevent core overheating, creating operational constraints that influenced every subsequent decision. Decay heat levels immediately following shutdown from 43% power operation totaled approximately 3% of full thermal power, representing roughly 20 megawatts of heat generation that required removal through the plant heat transport systems. While significantly less than normal operating thermal loads, this heat generation rate was sufficient to cause core damage if cooling was interrupted or significantly reduced for extended periods. The auxiliary cooling system for all three secondary loops was immediately placed in service following reactor trip, providing backup heat removal capability, while operators assessed options for isolating the damaged Loop C. The ACS was designed to provide adequate decay heat removal capacity through natural circulation and forced circulation cooling, but required proper thermal hydraulic balance to ensure effective heat removal without overloading any individual loop. Thermal hydraulic analysis during the event confirmed that two intact secondary loops could provide adequate decay heat removal for the shutdown condition, but required careful flow balance and temperature control to prevent thermal stress or overheating. The loss of 1/3 of normal heat removal capacity meant that loops A and B had to operate at higher thermal loads than normal, creating potential operational challenges if any additional problems developed. Primary system cooling continued through all 3 primary loops despite the secondary system problems in Loop C. The intermediate heat exchangers were designed to provide thermal isolation between primary and secondary systems, allowing primary loop operation to continue even when secondary loops were unavailable. This design feature was essential for maintaining core cooling while managing secondary system problems. However, continued primary loop operation required adequate heat removal on the secondary side to prevent primary system overheating. With Loop C secondary cooling unavailable due to the sodium leak, the thermal load normally carried by that loop had to be redistributed to the remaining loops. This redistribution required careful thermal management to prevent exceeding design temperatures in any system component. The decision to begin draining sodium from SHTS Loop C was made at approximately 22:40, roughly 1 hour after reactor trip. This decision reflected operational assessment that the leak would not self-seal and that continued sodium inventory in the loop would sustain the leak and prevent access for repair activities. Draining would remove the driving pressure for continued leakage while enabling eventual system inspection and repair. Sodium drainage operations required careful temperature control to prevent sodium solidification in piping systems. Liquid sodium solidifies at approximately 98 degrees Celsius, creating potential for line blockage if drainage operations proceeded too rapidly or if local cooling caused temperature drops below the solidification point. Drainage procedures included preheating systems and controlling drainage rates to maintain adequate temperatures throughout the process. The drainage operation was complicated by the need to maintain sodium in liquid form while removing it from a system that was no longer being heated by reactor operation. Normal system heating was provided by thermal input from reactor decay heat, but with heat removal interrupted by the leak, alternative heating methods were required to prevent sodium solidification during drainage. Sodium solidification concerns also influenced the timing of drainage initiation. Operators waited until reactor shutdown was complete, and decay heat removal was established through alternate paths before beginning drainage operations. This sequence ensured that adequate cooling remained available while preventing thermal transients that could complicate the drainage process. The ventilation system for SHTS Loop C was automatically shut down at 2313 by safety interlocks that responded to low sodium level indications in the loop evaporator. This shutdown was designed to prevent potential damage to ventilation equipment and reduce the spread of sodium compounds through building ventilation systems. However, the ventilation shutdown also reduced atmospheric mixing in the piping room, affecting the distribution of sodium compounds and combustion products. Ventilation system shutdown created operational challenges for subsequent inspection and cleanup activities. Without forced air circulation, natural convection became the primary mechanism for compound transport and atmospheric mixing in the affected spaces. This change in airflow patterns influenced where sodium compounds accumulated and complicated initial assessment of contamination distribution. Loop drainage operations were completed at 0:15 on December 9, approximately 2 hours after drainage initiation. The successful drainage removed the pressure differential driving continued sodium leakage while enabling operators to begin assessing the extent of contamination and planning cleanup activities. With drainage complete, the immediate emergency phase of the event was concluded. Following secondary system drainage, primary system sodium in PHT's Loop C was also drained as a conservative measure to eliminate any potential for continued heat input to the damaged secondary loop. This action ensured complete isolation of the affected systems while maintaining adequate primary cooling through the 2 intact loops operating with auxiliary cooling support. The drainage of primary Loop C sodium required coordinating primary and secondary system operations to maintain proper thermal balance and decay heat removal. Primary system drainage could only proceed after confirming that adequate cooling capacity remained available through the intact loops and that thermal hydraulic conditions would remain within acceptable limits throughout the drainage process. Decay heat removal following Loop C isolation was maintained through PHTS Loops A and B operating with their respective secondary loops and auxiliary cooling systems. This configuration provided adequate heat removal capacity, but required monitoring thermal hydraulic performance to ensure proper distribution and prevent overheating in the operating systems. The thermal hydraulic analysis during two-loop operation confirmed adequate heat removal margins for the decay heat levels present, but revealed sensitivities to operational parameters that required continuous monitoring. Flow rates, temperature distributions, and heat removal effectiveness had to be maintained within narrower operating windows compared to normal three-loop operation. Natural circulation effects became more significant during two-loop operation as forced circulation margins were reduced compared to normal operating conditions. Thermal driving heads and flow distribution required careful management to ensure adequate core cooling without creating flow instabilities or thermal stratification that could compromise heat removal effectiveness. Temperature monitoring throughout the operational transition revealed that primary system temperatures remained within acceptable limits despite the loss of one heat removal loop. Core temperatures, primary coolant temperatures, and heat transport system temperatures tracked predicted values for shutdown conditions with two-loop cooling, confirming that heat removal capacity was adequate. Secondary system temperatures in the operating loops increased moderately as thermal loads were redistributed following Loop C isolation. However, temperature increases remained within design limits and did not threaten component integrity or operational safety margins. Thermal performance monitoring confirmed that the remaining systems were capable of managing the increased thermal loads. Flow rate measurements in the operating primary loops showed stable performance throughout the transition to two-loop operation. Primary coolant pumps continued operating normally with flows maintained at levels adequate for decay heat removal. Secondary system flow rates were adjusted to optimize heat removal while maintaining thermal hydraulic stability. Pressure control in the operating systems remained stable throughout the event sequence. Primary system pressure was maintained within normal ranges by the pressurizer system, which continued operating normally despite the secondary system disturbance. Secondary system pressure in the intact loops was maintained by normal pressure control systems operating at increased thermal loads. The auxiliary cooling systems provided essential backup heat removal capability that enabled successful management of the event. ACS operation demonstrated the effectiveness of design provisions for emergency heat removal and confirmed that adequate cooling capacity was available even with one complete heat transport loop unavailable. Control room coordination during the stabilization period required managing multiple simultaneous operations including reactor shutdown, decay heat removal, loop isolation, and sodium drainage. Operators successfully coordinated these activities while maintaining adequate monitoring of all safety-significant parameters throughout the complex operational sequence. Emergency response procedures provided adequate guidance for the stabilization activities, but required operator judgment in coordinating multiple simultaneous operations that were not explicitly covered in existing procedures. The procedures assumed that loop isolation could be accomplished more quickly and with fewer operational complications than actually occurred during this event. Communication with off-site authorities proceeded according to established protocols for notification of operational events. However, initial notifications were based on preliminary assessments of leak severity that proved conservative as more information became available about the actual failure mechanism and consequences. Radiation monitoring throughout the facility confirmed that no radioactivity was released during the event. Secondary system sodium leaks pose no radiological hazard because secondary system sodium has no contact with reactor fuel or fission products. This confirmation was important for emergency response classification and public information activities. Environmental monitoring around the facility confirmed that no environmental impact occurred from the sodium leak. All sodium and sodium compounds were contained within the plant building, and no releases to the environment occurred. Environmental protection systems functioned properly to contain all materials within design barriers. Cleanup planning began immediately following stabilization of plant conditions. The sodium compounds accumulated in the piping room required removal using specialized procedures and equipment designed for handling reactive sodium compounds. Cleanup operations would eventually require several months to complete due to the chemical reactivity and distribution of the contamination. By the morning of December 9th, plant conditions had been stabilized with two-loop cooling providing adequate heat removal, the damaged loop isolated and drained, and initial cleanup activities initiated. The emergency phase of the event was complete, but investigation and cleanup activities would continue for months to determine the failure cause and restore the facility to operational condition. The stabilization period demonstrated both the effectiveness of emergency response capabilities and the operational complexity created when small component failures initiated system-wide response requirements. Operators successfully managed multiple simultaneous operations while maintaining reactor safety, but the event revealed the potential for minor failures to create major operational challenges through system interdependencies. The recovery of the lost thermocouple well tip from the distributor at the top of the superheater, on April 24, 1996, provided the critical physical evidence necessary to confirm the failure mechanism that had been theorized during the initial investigation. The separated component, approximately 15 centimeters in length, had traveled through the secondary sodium system following the fracture event, eventually settling in a low-velocity region where flow conditions allowed gravitational settling. Metallurgical examination of the recovered well tip was conducted at the Japan Atomic Energy Research Institute and the National Research Institute of Metals, beginning in February 1996. The fracture surface analysis revealed characteristic features of high cycle fatigue failure, including distinct crack initiation regions, progressive crack growth zones with striation patterns indicating cyclic loading, and final fracture areas exhibiting ductile failure characteristics. The microscopic inspection identified multiple crack initiation sites along the stress concentration region created by the 120-degree angle transition in the well geometry. These initiation sites exhibited the smooth crystallographic features typical of fatigue crack nucleation under cyclic stress conditions. The crack growth regions showed progression patterns consistent with stress intensity variations during operational cycles at different power levels. Fractographic analysis revealed that crack propagation had proceeded through approximately 80% of the wall cross-section before final fracture occurred. The progression rate varied with operational parameters, with more rapid advancement during high-power operation when vibrational loading was greatest. The final 20% of the cross-section failed rapidly in ductile mode when remaining material could no longer support even reduced operational loads. The metallurgical findings confirmed that the failure mechanism was high-cycle fatigue resulting from flow-induced vibration, exactly as predicted by computational fluid dynamics analysis of the well geometry and sodium flow conditions. Vortex shedding around the sharp taper configuration created alternating forces in multiple directions that accumulated fatigue damage over months of operation. Flow-induced vibration analysis conducted using computational fluid dynamics modeling revealed the specific mechanism by which the thermocouple well geometry created conditions for fatigue failure. Sodium flowing at 5 meters per second around the sharp 120-degree taper created flow separation and vortex formation that generated oscillating forces with frequencies in the range of 10 to 50 Hz. The vibration analysis showed that the well experienced symmetric vortex shedding from both sides simultaneously, creating complex loading patterns that could not be adequately addressed by existing design codes. The ASME Performance Test Code PTC 19.3 provided guidance for preventing resonant vibrations that could cause immediate failure, but did not address the cumulative effects of small amplitude oscillations over extended operating periods. Comparison with recommended taper geometries revealed that gradual taper configurations would have prevented the flow separation that initiated vortex formation. The sharp taper geometry used at Monju was intended to optimize thermal response time by positioning the sensing element closer to the pipe wall boundary layer, but this thermal optimization created the flow conditions that led to mechanical failure. The investigation revealed that design guidance available at the time of Monju construction did not adequately address the interaction between thermal performance optimization and mechanical durability under flow-induced vibration conditions. The 1991 Addenda to ASME Boiler and Pressure Vessel Code Section 3 Appendix N, published after Monju design completion, included provisions for vortex-induced vibration prevention that could have prevented this failure. Regulatory review of the failure mechanism revealed gaps in design code coverage that allowed optimization for one performance parameter to create vulnerabilities in another. Thermal performance requirements drove sensor placement and geometry decisions without adequate consideration of mechanical integrity under operational loading conditions. The investigation findings led to comprehensive design changes for similar instrumentation throughout the facility. All thermocouple wells with comparable geometries were replaced with designs incorporating gradual tapers that prevented vortex formation while maintaining adequate thermal response characteristics. The replacement program required extensive analysis to optimize thermal and mechanical performance simultaneously. Operational procedure modifications were implemented to improve detection and response capabilities for component degradation that might not produce immediate thermal or flow indications. Enhanced inspection protocols were developed for accessible instrumentation components, and condition monitoring programs were expanded to include mechanical integrity assessment beyond thermal performance verification. Training program revisions incorporated lessons learned about the limitations of thermal monitoring for detecting mechanical degradation. Operators received additional instruction on recognizing signs of component degradation that might not manifest as thermal transients, and procedures were modified to include component condition considerations in operational decision-making processes. The emergency response procedure modifications addressed the operational complexities revealed during the event management. Improved guidance was developed for coordinating multiple simultaneous operations during complex emergency sequences, and decision-making frameworks were enhanced to address situations involving ambiguous or incomplete diagnostic information. Alarm system modifications were implemented to improve integration of information from multiple detection systems during abnormal events. The modifications provided better correlation between thermal, chemical, and mechanical indications to improve operator assessment of failure modes that produced multiple simultaneous alarm signals. Communication protocol improvements addressed delays in initial event, reporting, and information management during emergency response. Enhanced procedures were developed for rapid assessment and reporting of event severity, with improved coordination between operational and regulatory notification requirements. The investigation revealed fundamental limitations in monitoring philosophy that assumed comprehensive thermal measurement could provide adequate protection against all significant failure modes. The failure demonstrated that instrumentation components themselves could degrade through mechanisms that remained invisible to the monitoring systems they supported. Design philosophy modifications incorporated recognition that monitoring system components required condition monitoring independent of the thermal performance they provided. The concept of monitoring the monitors became embedded in subsequent design and operational practices to address the systematic blind spots revealed by this failure. Regulatory framework evolution incorporated requirements for systematic evaluation of monitoring system limitations and component interaction effects during design review processes. New guidance required explicit consideration of how design optimization for one parameter might affect performance in other areas. Industry-wide lessons learned from the Monju failure influenced fast reactor design practices globally. The specific failure mechanism and contributing factors were communicated through international technical exchange programs to prevent similar failures in other facilities. Research programs were initiated to develop improved approaches for component condition monitoring in high-temperature liquid metal environments. The research focused on techniques that could detect mechanical degradation without relying on thermal performance indicators that might mask developing problems. The failure analysis revealed how sophisticated engineering systems could function correctly while containing systematic vulnerabilities that became apparent only under specific operational conditions. The investigation demonstrated that complex systems require monitoring approaches that address component interactions and failure modes that cross traditional engineering discipline boundaries. Quality assurance program modifications incorporated requirements for systematic evaluation of design assumption validity throughout component life cycles. Enhanced review processes were developed to identify situations where design optimization might create unintended vulnerabilities in other performance areas. The long-term operational impact of the failure extended beyond the immediate technical modifications to influence organizational approaches to system complexity management. The event demonstrated that small component failures could initiate operational sequences that challenged multiple systems simultaneously, requiring enhanced coordination capabilities. Post-incident analysis confirmed that the failure was preventable through application of design knowledge that existed at the time but was not systematically applied during the original design process. The failure resulted from gaps in design code coverage rather than limitations in fundamental engineering understanding. The forensic investigation established that accurate monitoring of bulk system parameters could not detect localized component degradation that proceeded through mechanisms independent of the monitored parameters. This fundamental limitation required recognition and compensation through alternative monitoring approaches. The systemic lessons learned from Monju influenced nuclear industry practices regarding instrumentation design, condition monitoring, and emergency response procedures. The event demonstrated the importance of systematic evaluation of monitoring system limitations and the need for monitoring approaches that could detect their own degradation. The investigation confirmed that engineering failure analysis requires examination of system interactions that cross traditional design discipline boundaries. Thermal, mechanical, chemical, and operational factors all contributed to the failure sequence in ways that could not be predicted. Through analysis of individual engineering disciplines in isolation, the Monju sodium leak incident ultimately validated the effectiveness of defense in-depth safety principles while revealing the limitations of monitoring-based protection strategies. The event confirmed that multiple independent protection layers could prevent serious consequences even when individual protection systems experienced unexpected failures.